So this session is going to be we had previous ones. We went into God's Word, looked in great detail in the Hebrew language. We just let God's Word speak for itself. And this time we're going to get more into the science. And part of this was our introductory session back in January. Almost a year ago. A lot of interest. How do you talk to people who don't have the same beliefs? So that's what we're going to do. I'm not going to read through it all here, but we'll get to it when we get to it. Just what we cover. So there's a lot of information you can see, and I'm going to have to go, in order to get through the whole thing, and especially the last few slides are really important, so I definitely want to get to that. So some of this is going to go through pretty quick. If you want to know more about it, I can send you the slides, so you can look at them later. If you have any questions, feel free to contact me. I did put my email address up there on the first slide. A little bit, when you start talking about evolution and that sort of thing, I think a lot of Christians are like, we can't go there, we shouldn't do that, but I think it's important that we do. If you want to have a discussion with somebody, like I said, it's very helpful if you have some knowledge, because I think a lot of people out there, secularists and evolutionists, think that as Christians we don't know anything, that sort of thing. So I think it can be very helpful if you can actually have an intelligent discussion with them. And like we said about apologetics, that's what about being able to give a defense for what you believe. And I've mentioned before, there's this thing, if you're confronted with information that you're not familiar with, or maybe they're being accusational, it can make you feel uncomfortable. That's called cognitive dissonance. So by studying these things, that should help alleviate that feeling. You can have confidence, you can keep talking with them, keep having that dialogue, and they might think, wow, maybe there's more here than what I realize. Is there something else I don't know? And that's a golden opportunity right there, because they're willing to talk. This information isn't required to be saved, of course, but it is good to know. And we don't do this to prove the Bible is right. We'll talk more about this a little bit later on, but if you use science to prove the Bible is right, and then later on that particular piece of science is proven to be wrong, they can argue, well, we just proved that the Bible's wrong too. Okay, so that isn't why we do this. The Bible stands on its own. Hey, Pastor? This button's not working now. Still doesn't seem to be working. That is exactly right. Thanks for bringing it up. Don asked, so science isn't completely settled and final? Yeah, we're going to talk about that more too. Many slides on that, actually. All right.
So much knowledge, wealth of knowledge that it froze my computer.
Okay. All right, evolution. When we hear that word, I think most people think of Darwin and going apes to man and that sort of thing, but there's three parts to it, really. There's cosmological evolution, which has to do with the origins of the universe, and once the universe is in place and the Earth is here. Then there's geological evolution, which talks about how things changed over a long period of time on the Earth, involves rock layers, fossils, carbon-14 dating, that sort of thing. And then we have biological evolution, and that's kind of what gets back to Darwin, monkeys to man, and that sort of thing. The other thing is that when you talk about evolution, it all has to be natural occurrences. You can't bring God into it at all. No supernatural type things. And we're going to be focusing on cosmological evolution right now. And then later on next year, we're going to talk about geological and biological evolution. Okay, we basically talked about this. This is kind of the actual definition of cosmology. It's a bunch of science that has to do with the universe. All right, this is going to start touching on what Don brought up earlier about changes in science and that sort of thing. So we're going to talk about some of the phases of science and how they changed over time. Back up one. So the earliest description of creation is the Bible. In the last sessions, we talked about days 1, 2, and 4, and that's kind of focusing on cosmology. Later on, there was the geocentric model, heliocentric, steady state, Big Bang theory, and now they're looking at changing Big Bang theory and going to the next thing. So, starting out with Genesis, I'm just going to kind of skim through this real quick. We talked about this a lot the last section. But in the beginning, God created the heavens and earth. In the beginning, there was nothing but God. He created everything from nothing. And he said, let there be light. Separate the light from darkness the first day. And he said that a day there means a 24-hour day, not long periods of time. Then he created the expanse, separating the waters above and below. We'll talk about what that might mean from a scientific standpoint. And then on day 4, God said, let there be lights in the vault of the sky, or in the expanse, or in the heavens. And that was the 4th day. So this is kind of a summary of the whole thing, including some of the days that we didn't talk about. Everybody believes this, right? So now some of the scientific early beliefs, the geocentric model, basically that is that the Earth is the center of the universe. And for a long time they looked out at the stars, the way the sun goes around. It sure seemed like, every day I look out, it looks the same, so it must be the center. And then they started to actually advance that idea using mathematics and that sort of thing. That was Ptolemy that started that. That was about 150 AD or CE. And that kind of persisted until like the 16th to the 17th centuries. Copernicus and Kepler came along and started advancing the idea, looking at some of the things that they were seeing. It's like, that doesn't really work. Then we have the heliocentric model, which puts the sun at the center of the universe, and the Earth is going around the sun. Again, that was developed by Copernicus around 1500, supported by Galileo and Kepler. And of course, the scientists at that time really had an issue with that. So yeah, there's a lot of opposition to that. Once a belief is firmly in place, so even though it was very scientific, really resisted it. Okay. He had his telescope. He was things, and out there and everything, they were different from the stars, and that really changed. And he was a Christian in the Catholic Church, but the church got involved with it too. He was actually tried by the Inquisition and found suspected of heresy. And he was actually sentenced to house arrest for the rest of his life for his beliefs. Orthodox Lutheran, but he was religious also. And a lot of people, I think that evolutionists don't think Christians are involved in science, but they were. And some of the earliest ones there were a lot of them. Even some of the ones in mathematics, like Fourier, he has some crazy math, but we use it all the time. And he was actually going to be a pastor. His dad was a pastor, but he got into mathematics. So not only did they see those things, but they were looking at the universe as a whole. And the Bible says that there was a beginning, but a lot of people believed at that time that the universe was static. It always was there, it always will be, it's unchanging except for going around the sun and that sort of thing. And that's called the steady state or static universe model. And that was around 1200s.
Go ahead.
Test. Okay. Thank you. That's better. All right. Get a drink of water while I'm at it. Just about ripped it out of my ear. Okay. And that steady state model persisted for a long time, even up to Einstein. Einstein made all kinds of equations, cosmological equations. You may have heard of the special relativity and general relativity and all that. In order to make the math work, he introduced the cosmological constant to prove that it worked. Later on, though, we found out that he made a big mistake, and he admitted that was one of the biggest mistakes of his life, as he had to change his views. So phase two, they noticed way back a long time ago that, I don't know if you remember from high school science or even elementary science, you shine a light through a prism, the white light goes in, splits it out, so you have the colors of the rainbow. And we're going to talk more about this in greater detail later, and so some of those slides that you have are going to talk about that. But they noticed this redshift in the spectrum of the lights that they were seeing from the stars. And it was not easy to explain, but they started to think, and I don't think the universe is actually static. I think it has to be, these stars and galaxies are moving. So that was kind of the beginning of the next phase. In 1924, Hubble, maybe I've heard of the Hubble telescope that was named after him. He also noticed that, and he started to actually quantify it in a more detailed way. And he was saying, yes, this is definitely happening. There was even another Roman Catholic priest that was looking at that. And he also said that. And again, in 1929, that was correlated between all these different people. They were all seeing that. So that was really hard for some people to accept. And not only is it expanding, but because of the amount of redshift, the expansion was actually accelerating. That was really difficult to explain. So how do they know that how far away these stars and galaxies are? It's not like you can take a tape measure or one of those wheels with the thing on it and drive up and down and forth and count how far, right? So there's a couple different ways, and one of them is called the parallax method. And basically what that means is, you can do this really easily right now. If you look up at the cross and hold your finger up there, and you look at it with one eye, then open and one eye closed, and then switch sides, you notice that your finger is very different relative to the cross all of a sudden. And then it has to do with the angle that your eyes are seeing it at, okay? So we call it, like if you're looking at a gauge or something and it looks funny, that's called parallax error, but that has to do with having 2 points of view looking at the same thing. So then you can use those angles and some trigonometry and find out how far away it is. So you can calculate it, okay?
That's on your handout, by the way?
Yeah, that's on your handout. So up to about 400 light years away, that actually works pretty well. But the universe is much bigger than that. As you start getting further away, those angles become so small that you can't, there's a lot of error that comes involved with it. So they had to come up with another way. So there's the brightness and the size method. When they looked at galaxies, and certain galaxies look very similar, there's like different classes of galaxies. So they started becoming familiar with it. Some of them are close, so using the parallax method, they could measure how bright they are, how big they are. So now when you have those same types of galaxies that are a long ways away and you can't use a parallax, you can still see them, but you can look at the size and the brightness of them. And using all this information together, that's how they determine, at least they think, how far away these galaxies are. So now we're going to talk about this redshift. Light is a very unique thing. It acts like a particle sometimes, and it acts like electromagnetic wave sometimes. So it has wave properties just like water and sound through air and all that. So you can see over here with the, whoops. Wrong button, whoops. It's kind of hard to see, but they put a red line there showing the distance between the wave crests or the wave troughs. That's called a wavelength. And everything, like I said, sound waves, everything has this wave property to it. So you can have a sine wave here. If you measure from that peak to that peak, that's the wavelength. If that frequency, if that sound, for example, a high pitch, it's doing that really fast, so it's a high frequency. If you look at that on an oscilloscope or some piece of electronic test equipment, it'll have a short wavelength. Lower sounds have a longer wavelength. Okay, so that's how you can kind of figure out what's going on, is by the wavelength. And also they can have an amplitude. This one has a larger amplitude. This is a little bit smaller, but you can have a high frequency, large amplitude, or small amplitude. They're independent. Now in the time domain, if you look, this bottom axis is time, and this is amplitude. All we want to know is what's the frequency or what's the wavelength. We don't need to actually have all this information. So by looking at it on a spectrum, where the x-axis is frequency, it's just a lot easier to see, well, it's a high frequency or low frequency, and we know what the amplitude is. And that works really good. In my line of work, I use this all the time, looking at electronic signals. Okay, you can use it for sound, all kinds of stuff. But for light, it's a little easier to look at it in a different way. We talked about the prism and looking at the different components of light. That's what a prism really does, is it splits the light up into frequencies. So a continuous spectrum of light would look like that. And if you have pure white light, that's what it's going to look like. But if your light is being generated by something that doesn't actually produce all those wavelengths, you're going to see these emission lines. And we see that in the laboratory all the time. If you have, say you have a blowtorch with propane, and you shine that light through a prism, you're not going to see all of the colors because propane burns with different, only specific elements, and it gives off a very particular fingerprint, okay? And then depending on the medium that you're looking at it's sort of like a negative image. Instead of an emission line, you can get an absorption line. These actually help a little bit because, you see, well, it's a green line there, but by looking at it this way, you can see, oh, it's in the bottom side of the green line and getting close to the blue. So those are just different ways of looking at the same thing. And out here, the purple is higher frequency, shorter wavelength, and the red is lower frequency, longer wavelength. And as I started to talk about what happens if you heat these gases or whatever, they get excited, the electrons go into a higher orbit or energy level, and then they collapse and they go out again. They're getting all worked up, and as the electrons fall to a lower energy state, it gives off a photon. That's what produces light. So that's what this is showing up here. As you go from energy state 2 to back down to energy state 1, it gives off a photon. And so this shows right here, and you should have that in your handout too, that for different elements, this up here is hydrogen, it gives a very specific fingerprint. There's one red line way down here, and then there's one up in the blue with nothing in the middle. And I've had to work with hydrogen where I work. We work with fuel cells that use hydrogen and oxygen and that sort of thing. And if you have a hydrogen fire and you look, you cannot hardly see it. It is there, it burns incredibly hot, it's a real thing, but you can't see it. It's basically invisible unless you look at it with a thermal imaging camera. That sort of thing. It's not like propane where you can actually see it. So helium here is a little bit different. You start getting down to different elements, carbon and that sort of thing. Now you see all these different lines. And so it's sort of like a signature of what that element is. And they can use this to look at stars. They look at the spectrum of it, and they say, oh, well, there's definitely hydrogen and helium there, but there's not a lot of anything else. And that's partly how they figured out that suns or stars are undergoing nuclear fusion, combining hydrogen to make helium and giving off tremendous amounts of energy. That's how they know that, is by looking at its frequency spectrum. Okay, now, with sound waves, you may have heard Doppler effect before. If somebody is driving by, they've got their window open, they're listening to the radio, and you can hear some song. As it approaches you, it sounds one way, but as it's going past you, all of a sudden it sounds very different. Or maybe like a train whistle or something like that. It changes the pitch, and it has to do with the velocity that they're traveling. And what happens, if this is the sound source, and it's going this way to the left, the sound waves go into the air, and it gets compressed because of the velocity. So that produces a higher pitch or shorter wavelength. And then behind, as they're going away from you, that's getting stretched out, which produces a lower pitch and a longer wavelength. Even though the frequency of the sound in the car is constant, as it's moving away from you, you experience this compression or expansion of the sound waves, which changes the pitch from your frame of reference. It sounds like it's changed. Okay, so that's Doppler effect. And you can see that if you look at the spectrum for audio waves and that sort of thing, it'll shift those tones to the right. If it compresses it, it shifts it to the right, so those spikes move over. When you listen to it as it's going away from you, it actually shifts those tones to the left, indicating a lower frequency, longer wavelength. Well, with light, I need to point this out to you. So that happens with Doppler shift. That happens as the source is moving through space. The space is already there, they're just moving through it, and it has to do with the air. Now, with light, a similar thing can happen. And what they noticed with this redshift is they saw the signature of hydrogen and helium, but it wasn't right where it was supposed to be. It was shifted to the red side of the spectrum. So you think, oh, that's kind of like a Doppler shift, but how can that be? Well, it means it has to be moving. That's where they realized that that was going on. But it's a little bit different because, when you think of expansion of the universe, it isn't that all this space was out there and the stars and everything are moving through it. What's actually happening is space itself is being stretched. So it's a little bit different, and that will come up later. But this redshift is occurring because of stretching of space, not movement through space. Okay? So as they look at things that are very close, there's very little redshift. They start looking at further away, using those methods to measure distance to stars and galaxies, the redshift became more. The further out into space they looked, the redshift was even greater. Okay, so that's how they know the universe is expanding and it's accelerating. The rate of expansion is not constant. And that really threw people for a loop. I mean, how do you explain that, right? Okay, so we talked about that. Okay, just real quick, because we're going to talk more about this later, but because we got to get through these things and keep questions down to a minimum, but this is kind of important. Does anybody have any questions about this real quick? Okay. So, knowing that, they're like, okay, it's going out. What if this was like a movie and we played it backwards? And they started to think, well, if it's expanding out from someplace, it came from someplace, and if you move that movie back in time, it must have all started at a point. And what they realized was if you look this way in space, you see the same thing as when you're looking at that way in space. So it's expanding in all directions. So if you move that all backwards in time, it must have all started at a very small point. And they call that the primeval atom. Not atom like the Garden of Eden, but an atomic atom. Okay? And just like we talked about, whenever you come up with new ideas in science, there are people that absolutely hated that idea. There's a lot of scientists that hated that idea for a very long time. And one of them, his name is Hoyle, he really hated it because he was not only was he atheist, he was anti-religious. That takes it a step further. He hated that idea because that's what it says in the Bible. There was a beginning. And for a long time, they had this steady state model that was in place for a very long time. It was very entrenched. And so when he heard there was a beginning of the universe, he absolutely hated it. And he fought against it. And ironically, he was on a radio talk show or whatever, talking about this, and he kind of made fun of the idea. So he was like, yeah, so you start out with nothing except this little dot, and all of a sudden there's this big bang and everything's exploding and expanding. So he meant it as a derogatory term, but it stuck because it's now still called the Big Bang Theory. Not to be confused with that TV show, right? And so that happened in the 1950s. He went back and tried to reformulate the steady state model to keep it alive, but it just wasn't working. And then finally, he abandoned it. And ironically, later, Hoyle said, he was very anti-religious, a super intellect has monkeyed with physics. And not just this, but with chemistry and biology, and we'll talk more about that later when we get into biological evolution. If you look at that, there is just no way, even from a scientific standpoint, the way that they talk about evolution and biology and all that, it just does not work. It can't. There's this thing in the second law of thermodynamics about entropy. There's just no way it should work. We'll talk more about that later. But he even said there are no blind forces worth speaking about in nature. In other words, it can't just happen by itself. Now, I don't know. I tried to do some research to find if he actually became a believer or not. I didn't really find anything definitive, but some commentaries say that he kind of came around to the idea there must be a God, because this can't happen otherwise. Another interesting thing is this junkyard tornado. Imagine you have all kinds of junk out in the junkyard. This tornado comes around, whipping stuff around, and magically a 747 comes out of it, right? It's not going to happen. Even simpler than that, you take a nice car, you park it out in the Grove and leave it for 10 years, it turns into a piece of junk. If you take a bunch of junk and throw it out in the Grove and walk away and come back 10 years later, it's even more junky. You don't get a nice car out of it, right? I wish that would happen, but it just doesn't. It just does not go that way. And some of these things, I put little references down there. If you ever want to look it up, you can read that stuff yourself. All right, so now some scientists are saying, okay, well, there's this Big Bang thing. Let's look into that. So they thought about, well, how could this possibly work? What would that look like? You have this initial bang somehow. We don't know where all that energy or matter came from. How did it get into that point? No idea. Why all of a sudden did it start? But let's just pretend it did. What would that start to look like? And so they predicted that there would be all kinds of electromagnetic radiation and that sort of thing. And you're going to hear, if you study this at all, you're going to hear this term, this cosmic microwave background radiation, or CMB. So they predicted that that would happen. Basically, I don't know if any of you even remember this anymore, but the old black and white TVs and stuff, if you unplug the antenna, you just get this white dots and snow and sound, right? That's just random electronic noise is what that is. And they predicted if they had a radio telescope and looked out, they should see that. And they were very careful that it wasn't their instrumentation that was making that noise. They were picking it up from outer space. That's what they thought should happen. And some guys back in 1965, Bell Telephone Laboratories, they used a special instrument for doing that, and they actually measured it. So into the 1960s and 70s, there was still some battling about that. They tried to explain it away. They couldn't. And finally, in 1978, those guys got the Nobel Prize in Physics for that, settling the science. There was this cosmic radiation out there. Proves the Big Bang happened. It was settled science. We have a new science now. Get over it, you Big Bang unbelievers, okay? There was quite a struggle there. Just real quick, I kind of talked about it already, but it's sort of like that snow on the old TVs and stuff. And so this is kind of a picture of what that looked like. And it's very uniform. Just a few little red dots there, but it's very uniform. And this kind of comes back to bite them later. They're like, you know, it's like if you have a bathtub and you put hot water on one side and cold water on the other, it takes time for all that to mix and to even out until you finally have one big tub of warm water. Okay, you can't have pockets of high and low energy. And you would think naturally as this thing occurred, you're going to have pockets of, the red areas would be a lot bigger. That would indicate areas of high energy. You'd have some blue, you might have some green, you might have some yellow. It should be kind of, pockets of these uneven energy states, but that's not what they saw. And so that's going to come back later too. One of these days I'll learn how to push these buttons. Okay, so now back to the Big Bang Theory. This is kind of how it went. So starting over on the left side at T minus negative infinity up to 0, was there really even time before 0? They think that there was no space, there was no time, there was nothing except this tiny little dot that held everything, and it was just this small point, and all of a sudden, at t equals plus 0 to 1 second, all of a sudden, it began to expand. Not expanding into space, but creating space, expanding space as it went, and all this energy is just coming out. Super bright, just energy expanding at an incredible rate. At 3 to 5 minutes, it's expanded so much, but now it looks a little bit different because shortly after that, we know this to be true, that energy and matter are actually interchangeable. You may be familiar with Einstein's equation, E equals mc squared, that says energy and mass are interchangeable. In the nuclear power program where I was, they actually measured that. It's called mass defect. As uranium atoms are split, the mass, suddenly this mass appears. And if you're doing fusion, mass disappears and the energy comes out, and it's measurable, okay? So that's what they're saying. And as these molecules or protons and neutrons and that sort of thing are forming, it starts to block the light. That's why it's starting to look kind of peppered there. Okay, and within 5 minutes, it's 53 million kilometers, or about 50 million miles across within 5 minutes. So it is really booking, right? I mean, just, okay? So now if we go out further, it's kind of hard to represent it that way. So they've come up with a really cool way to look at it. So back here is the initial dot exploding, white light. Here's that cosmic background radiation. As you're starting to get conversion of energy into matter, and it starts from outside, it would start to block that light. And so then you have this dark period. So first there was light, and then it got dark. And then after, 400 million years or so, right here, you start getting the first stars forming. We'll talk about how that happened, supposedly. And as time goes on, you get galaxies and all that kind of stuff. But you'll notice there was this rapid expansion initially, and then it kind of is expanding, but not that great. And then all of a sudden, later on, where we are now, way more redshift. So the expansion is accelerating. How much is it going to accelerate? How fast? Is it going to go on forever? That's kind of things that they're talking about. Some people think that, well, at some point, it's going to have to slow down, and then we'll end up with this big crunch at the end. But that's all theory yet, too. So the size of this thing, and this is all happening in 3 dimensions, but it would just be impossible to see. So they're only showing one direction here, but this is occurring in all 3 dimensions. And so they think, based on the way their measurement techniques, that it is 13.77 billion light years across. That's how big the universe is. Okay, and since light travels at the speed of light, they, instead of saying billions of miles and stuff, because it would just be an astronomically huge number if you're looking at miles. So they call it light years. And so if you do that, you can go back, and that means 3.77 billion years ago was when the Big Bang started. Of course, we know from the Bible, all of this happened in 6 24-hour days. That's a pretty big spread to kind of come to some sort of an agreement, right? How do you bridge that gap? Well, some creation scientists have, using Einstein's laws and some of the other things they've learned about, and looking at the Bible, they think they might have a way of explaining that, and that's what we're going to talk about at the end. Okay, I think that's it. So here's just a real quick storyline. Big Bang starts there. Start out with protons, neutrons, and that sort of thing. You get hydrogen and helium. Somehow they get compressed. You have nuclear fusion, which is not easy to do, but somehow it happened. You start getting stars. Later on, stars explode. You get supernova. Parts get recycled. More stars, galaxies. Because, somehow we went from hydrogen and helium, which is 1 neutron, 1 proton, or 2 and 2. You get all the way up to uranium and plutonium. You've got hundreds of these things. How did that happen? Okay. Their way of explaining that is if you have stars explode, that's a supernova, creates pressure waves, and then you can force nuclear fusion in nearby gas clouds and that sort of thing. That's what that recycling is talking about there. Eventually, you start getting rocks and stuff, and we get formation of solar systems, and we'll talk about that. So this is just sort of a summary of what we just talked about. Okay, I'll bring this up real quick right here. So they said that it's expanding, right? Well, something must be forcing it to expand. They don't know what that is. They can't measure it, so they know it's some sort of energy, but we can't see it, so it's dark energy, and that's their answer to that question. But we'll talk about that more in a couple of slides. Okay. Yeah, I want to point out right here. So there are some real big questions. There's a lot of them, actually, and we're going to talk about that. They don't have any other theories, though. I mean, it's one thing if you have a really solid theory that goes against what's been in place, that's a big struggle in itself. But if you have a theory that's got a bunch of problems with it, it's really hard to advance it because, they're like, what about this? What about that? I'm not buying it. Okay, so right now the Big Bang Theory, it's in place, but it's got some problems. But they got to keep going with it because they don't have anything else. Okay, and that's the way science is. That's not to ridicule them or anything like that. It happens even in the engineering field where I'm at. Okay, but in reality, it's a working theory. They'll try to tell you it's settled science, but it absolutely is not. And that gets back to what you're bringing up, Don, that it's not settled science. Okay, so kind of pictorially, I'm going to go through how our solar system got here. So start out with a gas cloud. You have a center of mass that starts to pull things together inward. You get a collection of hydrogen and helium there. And somehow you get this branch here. You start getting nuclear fusion. A star is born. Okay. You have a star in the center of this massive gas cloud that's, many, many light years across. It starts to bring stuff in. Then it starts to look like this. There's the sun, and you have all this stuff out here. There's this thing called a frost line. That's sort of like the dividing line between being warm and being really cold. Okay, and they call this a protoplanetary disk, and that's where the planets are eventually going to evolve from. Okay. Then as time goes on, you're going to have some local clumping of these particles. They're going to suck in more and more. They get bigger, and pretty soon those are the things that become planets. Okay, now, if this is over here and all these particles in this orbit are all going the same speed, I'm not sure how these particles end up here. But that's what happens apparently. This process takes about 1 million years for that to happen. Now, to think about that a second, there weren't actually any witnesses to this, but that's the way they are explaining it. Eventually, you have what we see today. We've got a sun, we've got some rocky planets, we've got some gas giants. We're going to look at that a little more closely. And so this can take anywhere from 10 to 200 million years for that to happen. You do have some leftover stuff in here. Those are asteroids and comets. And they think that our solar system is about 4.5 billion years old. So that's about 1/3 of the total age of the universe since the Big Bang. Okay. So now I'm going to do a quick look at some of our residents in our solar system. I'm going to have to hurry up here. Pluto. Notice that I said humor me, please. All right. When I grew up, Pluto was a planet. Since then, Pluto is not a planet. Maybe it's a dwarf planet. And I'm like, where'd that come from? Somebody's just trying to, become famous or something. But anyway, it's pretty small. It's a long, long ways away from the sun. It's like 3.2 trillion miles or something like that. 1 year on Pluto is 248 Earth years. It takes that long for it to go around the sun one time, and it's because it's so far away. The gravitational pull's not very strong. If it went any faster than that, it would fly off into space. If it was any slower than that, it would crash into the sun. Okay, so stable orbit right there. It takes that long to go around. If you look at the atmosphere and all that stuff, it's not habitable. There's just no way. Okay, Neptune, and I had some help with some of my grandkids on some of these pictures too, so thank you. But anyway, that was discovered in 1846. Can't see it with the naked eye, but they had a telescope and they noticed it. Really kind of pretty, but the atmosphere is water, ammonia, and methane. Pretty cold. Wind speeds over 1,000 miles per hour. I wouldn't want to be there. No, not habitable. That was cool. Uranus or Uranus, however you want to say that, 4 times wider than Earth, so it's really big. These are some different images from the different space probes that we had out there and space telescopes. Even though it's way bigger, the gravity is less, so you would weigh less on Uranus than you do on the Earth, and that's because it's a gaseous planet, so kind of a gas giant. Still really, really cold, lots of wind, and the weird thing about this too is it rotates on its side, which is very difficult to explain because the idea is you got this planetary disk, it's going around in a circle. As things combine, all the planets should be kind of spinning that same way. They all do, except for this guy. How in the world is it tipped 90 degrees roughly, spinning the wrong way? That's pretty tough to explain. And again, not habitable. Atmosphere, methane, hydrogen, helium, not going to work. Saturn, really big. You can see Saturn without a telescope. I don't know if anybody's ever tried to do that. If it's a kid, you ever looked at the stars or had a telescope or anything. You can see Saturn without a telescope. It looks like a star. You look through a basic telescope, you can actually see the rings. It's really cool. I'm thinking maybe this summer might be kind of fun to have a star party or something. Bring some telescopes out and show the kids, and hopefully we can see Saturn and Jupiter and some of those things. But we'll see. Only takes 29 Earth years to get around, but that's because it's closer to the sun. The path is shorter. Gravitational strength is stronger, so it has to go faster to stay in orbit. Really pretty, but really awful atmosphere. Metallic hydrogen. Ouch. Okay. No way. Nobody's living there. Jupiter, 11 times bigger than Earth. Also a gas giant. There is a solid core, but it's, if I remember correctly, it's not a whole lot bigger than our moon. The rest of that is this toxic, nasty atmosphere. So if you were to stand on the outside of Jupiter, because of all that mass, you would probably weigh like 600 pounds. But if you get down to the solid core, you're only going to weigh about what you weigh now. But the atmosphere, there's so much mass above you, it would be absolutely crushing. Just so much there. There's no way. It's nasty, plus it would just smash you. There's no way you're not living there. It does have some big moons there, and if you look at it through a telescope, you can see the moons of Jupiter too, and you watch them every night, and they change position. You can see it. It's really cool. Mars. It's about half the size of Earth. We've sent lots of probes there. It has 2 moons. Now we're starting to warm up a little bit. It can be anywhere minus 200 up to 70 degrees, so we're getting closer, but still not going to live there without some sort of help. Here's some pictures. Kind of cool, but kind of like, you know, when I was a kid, I wanted to be an astronaut. I'd love to go into space and all that, and I'd love to go visit the moon and whatnot. But as long as it takes to get to Mars, to have that scenery, Okay. One interesting thing about it, though, is it has one of the largest volcanoes in the entire solar system on this planet. Okay. And there's also, it looks like, if you look at the geology of it, it looks like there was water at one time, a lot of water. There's indications of floods there and stuff. Not sure what to make of that. So then they think, well, if there was water there, then maybe there was life there at one time. You know, it's not going to be life like we know it. Probably, if there was something, it'd be some little amoeba or something. I don't know. So I don't know. Next, anybody know which planet's next? Earth. Yeah, Earth. Wow, look at that. The diameter is about 8,000 miles. We're about 93 million miles from the sun. We are orbiting the sun at 67,000 miles per hour. Doesn't feel like it, but because of the distance that we have to go, though, it takes about 365.256 days. And that's why every 4 years we have it's a leap year, right, to make up for that little bit of a fraction there. Okay. One moon, definitely habitable, obviously. And now looking at some of the pictures of Mars and some of those other things, I thought, well, I wanted to have a really cool slideshow to show what Earth looks like, but I just don't have time for it. But a little bit different from Mars. Look at that. Absolutely beautiful. Right? God loves us, right? Man, incredible. There's some not so great places too, but let's focus on that, right? Okay, the moon, it's only 1,000 miles across. It's not habitable either. We're going to talk about this a little bit later, but there's some really interesting characteristics of the moon that kind of play into. It's like, well, if what we see is true, then how can billions of years be true? That doesn't make any sense. One thing that kind of comes up too is if you look at the near side of the moon, there's no such thing as the dark side of the moon because all sides of the moon do see light at some point. It's just that the one side is always facing it. It's not spinning relative to us. So it's the near side of the moon and then the far side of the moon. They look really different. It's just smattered with all kinds of impact craters and that sort of thing. Where this side doesn't have as much, but there are some, and some of them are quite big. And that kind of brings up some questions later. How can that be? Next, we go to Venus. It's about the size of Earth. Carbon dioxide and nitrogen mostly. 900 degrees on average. It's the hottest planet in the solar system. It's even hotter than Venus because the atmosphere traps the heat. Mercury doesn't have an atmosphere, so on the side facing the sun, it's very hot. The side away from the sun, it's very cold. Venus doesn't have that problem. It's always hot everywhere. The Soviets did land some probes there. They took some pictures. They didn't last very long because it was so hot, but that's basically what they saw. You know, it's kind of like Mars. Be cool. I went to Venus, but all right, let's go back. Okay. No way. There's no way it's habitable. Then we finally get to Mercury. Very small, about 1/3 of the size of Earth. Again, it kind of looks like the moon, actually. Very little atmosphere there because it's just constantly being stripped away by solar radiation and the solar wind and that sort of thing. And again, it's not habitable. Then we get to our sun. It's a star, yellow dwarf star, so it's kind of average size. But it's over 100 times bigger than the Earth, so it's huge. Mostly hydrogen and helium. Again, they can determine that not because they went down there and took samples, right? Because it's like 3.6 million degrees Fahrenheit. You're not going to take a sample of it, but they look at the light spectrum, and that's how they can tell that. Just for a second, it's like, well, there is a temperature range, though, anywhere from 11,000 up to that, but there are some dark spots there because of the chemical reactions and fusion and all that kind of stuff. So there are temperature variations. Definitely not going to live there, though. Here's an interesting thing, too. We get these solar flares, which they can see, and we can also detect that on Earth in multiple ways, but one of them is the northern lights. Those solar flares and the radiation that comes from that interacts with the Earth's magnetic field, excites a lot of those atoms in there, and in the ionosphere and the troposphere and all that stuff. When they get excited, they give off photons, and we get this marvelous light show here. I don't know, has anybody ever actually seen the northern? Yeah, okay. Really pretty, really pretty. When I was on a farm back in Minnesota, I was walking out by a field. It was dark out wintertime, absolutely beautiful, clear night, and I just happened to look up, and it was huge, absolutely beautiful. It stopped me right in my tracks. I'm like, wow. So, yeah, okay. So here's kind of the relative sizes. Here's Earth right here. Now the distances are not to scale, but the sizes are. So for reference, the sun, it's so big it's not even on the thing there. So if the sun was the size of a basketball, the Earth would be about 1/16 of an inch or 2 millimeters roughly, tiny. Tiny. It would be 25 yards away. So just absolutely massive. We'll talk a little bit more. In between Mars and Jupiter, there's this asteroid belt. And then way out at the end, there's this thing called the Kuiper Belt where some of those asteroids live. Okay. I'm going to skip these next slides, or at least I'm not going to talk much about them, but there are asteroids. Basically, asteroids are chunks of rock that are floating around in the asteroid belt and way out in the Kuiper Belt. There's some issues with that. For one thing, they say it's left over. Don't really see any clumping in the asteroid belt like they say happened. We don't see that. There's also issue with how to become rocky. It's supposed to be dust that collected and then built up and then turned into a solid. How's that going to happen on a small object like that? But okay, comets is the other thing. I will mention this because this will come up later. Unlike asteroids, which are rocky bodies, comets are dust and ice bodies. The reason they have a tail like that is because as they approach the sun, solar wind, solar radiation blows off some of those loose particles and it has a tail. So as it's going towards the sun, the tail is behind the body of the comet. As it goes around the sun and starts going away, the tail is actually in front of it because all those particles are blowing away. The tail doesn't follow the body because it's going so fast. The tail is there because the sun is blowing material away. Okay? So eventually, those comets should shrink down because the material is getting blown away. But they're there. You can see that the orbit of a comet is very different from orbits of planets. So since the comet shouldn't be there anymore after billions and billions of years, they theorize that there's some sort of a reservoir of comets that get spit out every once in a while. And that's how we can still have them. And it was a guy by the name of Oort that came up with that. So somewhere out there, there's an Oort cloud that supplies us with comets. Okay, we'll talk more about that in a little bit. Okay, there's the Kuiper Belt. It's way out there past Neptune. There's Pluto. Pluto has a very elliptical orbit and actually overlaps the Kuiper Belt, so that's why Pluto's not really a planet anymore. It's a Kuiper object, and there's a bunch of other ones out there about the size of Pluto too, but you just don't hear about them as much. Here's a picture of what that Oort cloud might look like. Our solar system is here. We got the Kuiper Belt, and way out there is this theoretical Oort cloud. They've never actually seen it. I'm kind of ribbing it a little bit, like they made up this Oort cloud. It could be there, maybe. It doesn't matter if it is. I mean, it doesn't change anything from a creationist standpoint. It's no big deal. But that's one of those things you would never want to base those types of theories to prove the Bible because later on it could be proven wrong or whatever. So we just have to say, yeah, maybe it is, but maybe not. And again, using the technology we have, they've never seen anything to support that theory. I mean, there's just no actual proof that it exists. Meteorites, meteors, those are chunks of rock that actually come to Earth if they burn up. If you've ever seen shooting stars and that sort of thing, those are little chunks of rock. They come into the Earth's atmosphere. Some of them burn up and don't make it. Some of them do land on the Earth, and that's how they can they find them. They're very distinctive in how they look. And then they can analyze them and see what they're made out of. And that's what a meteor shower is, if you've ever seen anything like that. They're really cool if you get a chance to watch them sometime, just to see them. I mean, they are screaming and they go across the sky like in a fraction of a second, and they're, I know, just very tiny little pieces make it a spectacular show when they come in. Okay. Okay, so where are we in this whole thing? This is a galaxy cluster. Inside of there is a galaxy. It's a spiral galaxy that's kind of similar to what ours looks like or what we think about, because we haven't been actually outside of our galaxy to take a picture, a selfie or anything like that, but it's what we think right now. So now zooming in a little bit, our galaxy is called the Milky Way galaxy. The Milky Way galaxy isn't something that's out there. It's something that we are a part of. And they think that we're situated in the arm of our Milky Way galaxy. That's what it looks like anyway. Has anybody actually seen the Milky Way galaxy? Tom? Okay. I've seen it. And on a really, really clear night, when you don't have a full moon or anything, and you look up, this is what it looks like. And it goes from one end of the horizon to the other. It is absolutely beautiful. It's amazing when you look up at that. And the first time I ever saw it, I was a kid. I was outside and looking at stuff, and my mom came out. What are you doing? And I'm like, oh, I'm looking at the stars. And she goes, oh, look, there's the Milky Way. And I'm like, what? She's like, yeah, that's the Milky Way galaxy. That's what we live in. I'm like, Mom, wow, that was pretty cool. How'd you know that? And I'm like, that was the first time that I ever actually saw it. It was incredible. Okay. Now, we've already kind of alluded to some of the problems of the Big Bang Theory. Now we're going to go through them more step by step. And this is not all of them. I made a list of them. The ones that I came up with, there's about 17 of them. And some of them are really complicated, and we just don't have time to talk about all of them. But here are the ones that are probably the easiest to talk about, and the ones you might hear about if you're talking about somebody who is into Big Bang Theory and cosmological evolution and that sort of thing. All right, so the first one, the experimental method in applied science versus historical science. Okay, so what is science? When they say the science is settled, what does that actually mean? The definition of science basically comes from this Latin word. It means knowledge, awareness, and understanding. Whatever it is, if that's the truth, that's knowledge and that's science. Even if you don't like it, even if you don't understand it, if you do your scientific method and you find out that's what it is, that's what science is. And they, evolutionists accuse the creationists of not being scientific, but as we've already seen, even amongst the scientists, when they argue about, well, you can't debunk our theories and all that, that's not scientific. You get the confirmation bias, cognitive dissonance, all that, that plays into it too, and they accuse us of not being scientific when they do the same thing, okay? Back up. Okay, so there's different fields of science. There's natural hard sciences, biology, physics, that sort of thing. Social sciences, psychology, a little more touchy-feely. If you drop a rock from this height, it always falls at the same speed, and it always takes a certain amount of time to get there. You can repeat that experiment over and over. When you're dealing in psychology and dealing with people, you think, well, this is a certain situation. They should act like that. What is up with this person? I don't get that. It's a totally different thing, even though it's science. Formal sciences has to do with mathematics and that sort of thing. That's a thinking type science. They have rules and regulations. We can use mathematics to describe things in the real world, but mathematics don't determine what happens. It's just a description of what happens. And then we have applied sciences. That's the field that I work in, engineering. That's more of you take the things that you figure out in science, and then how can you actually apply it in the real world? Now, in engineering, you do some experiments and do some theory and that sort of thing too, but it's really more of an applied thing. So it better work. If you come up with some wacky theory and you build something based on that and find out that your theories were wrong, you either kill somebody or cause a lot of damage and break stuff, and you can't have that. So that's the world that I live in. Not to say I haven't broken a few things, but because there's always the things you don't know that you don't know that you don't know. Okay, so the scientific method. In my world, definition one is a scientific method. And I'll have a picture of it too later that kind of shows it. But there's a lot of steps there. You come up with ideas, you have theories, like how can we test that theory? So you come up with a plan about how we're going to test it. Make sure the test is actually valid, that you're not introducing other unknowns in there, you're not lying to yourself. You want to know what the truth is. Whatever it is, you want to know what it is. So you got to be very careful how you set up your experiment. And where I work, we've actually had classes on that, just how to set up an experiment. Okay. Then you test it by conducting experiments. You measure the results of that, whatever it is. And there's been a lot of times we've taken data and it's like, I was not expecting that. What is going on? So you got to go back and look at your experimental setup. Sometimes your experimental setup causes problems. Those are called experimental artifacts. You don't want those in there. You lie to yourself. Okay. Then you analyze the results. You can draw conclusions, and then you can present your findings. You might publish things in a professional journal. In my field of work, we have like IEEE, it's called. It has to do with electrical engineers, Institute of Electrical and Electronic Engineers. You submit a paper. It's peer-reviewed. Is this something that's worthy of looking at? If it is, it gets published, and then everybody gets to read it. They look at it and like, that was junk. You need to redo this. You don't get published. Okay? Then after it gets published, other engineers will look at it and say, that's weird. I think I'm going to test that myself. So now you get independent research that goes out and looks into it, and they're like, yeah, we get the same results. You might get somebody else that says, I got different results. Your experiment was missing something, and here's what it is, and they get to publish a paper. Okay? But in some realms of science, you can't actually do experiments. Say, for example, you're a biologist, you want to go out, or maybe they're not a biologist, but a person who studies animals and that sort of thing in the wild. You want to know about why these lions and tigers and stuff, their population is doing a certain thing. So you go out there and you watch them. You don't go out there and mess with them for a couple of reasons. One, now you're introducing experimental artifacts into your experiment, and you might get eaten. Okay, you don't want to do that. That's an observational science kind of thing. You just have to sit back and watch and just see what happens. You have no control over that situation. Okay, so that's where these other definitions kind of come in. Then there's other sciences, which we'll talk about in just a second, that have a different one. Notice these steps are a lot shorter. They'd say, well, you also test your hypothesis, but they don't necessarily do that by experimentation. There's other ways of doing that. If you have a theory about something that's going on over there, you might be able to do an experiment in the lab to kind of simulate that, but it's not exactly the same thing. Okay. We already talked about that. This is that flow. Sometimes you do these tests, you look at the data, did it make sense? Nope, you got to go back and troubleshoot until it does make sense, and then you publish it, and then they do through the same process. And finally, when everybody agrees, yes, this is the way it works, the explanation makes sense, that's when you can kind of say the science is settled until something else comes along, and then you have to repeat the process, right? Okay, I kind of talked about this already. Observational science, historical science. This is where like cosmology, astronomy, and that sort of thing, archaeology, paleontology, you can't go back in time. There weren't any witnesses. All you have is what you're looking at and your interpretation of it. There were no witnesses. You can't do experiments on it. You can't go back and repeat that whole thing, especially if it's millions of years. How are you going to conduct that experiment? So you can't really apply the experimental method, strictly speaking, to some of these fields of science. Now, if you look up scientific method on the internet, you'll come up with that definition one that we talked about. I saw some YouTube videos of astronomers talking about the scientific method, and they're like, yeah, that's the scientific method. I'm like, well, that's your version of the scientific method. From my field, that is not very scientific, it's guesswork. But not to be disrespectful, and I'm not talking about that in terms of creationists versus evolutionists. I'm talking about that as an engineer to an astrophysicist. Just saying. And then cosmology here, and this is from an astrophysicist who actually says cosmology is a historical science because when we look out into space, we look back in time. It's historical. You can't do anything about it. All you can do is interpret what you see, okay? Again, we talked about naturalism, atheism. Theistic is God. Atheistic means no God. They could even be agnostic or whatever. They might even be Christian scientists, but when they're doing their explanation scientifically, they have to leave God out of it. Okay. All right. Okay. Next problem. What came before the cosmic egg, this Big Bang? Okay. Just real quickly, what caused it? Is our universe the only one? They don't really have an answer, is the bottom line. One thing you'll hear about is quantum fluctuations. Quantum mechanics is another branch of physics that came out later on. That's one of those things people had a real heartache with. It's what they call a metaphysics. It's sort of one of those weird, spooky things. Einstein even talked about string theory, which is spooky action at a distance. Saw some really weird things. You have electrons that go around the nucleus of an atom, right? And those electrons have spin. If they could get one to flip, the other one automatically flipped too. And they're like, that's interesting. Must be some sort of electric field that causes that. So they got this pair of electrons. They're spinning, they know like they push this electron way away somewhere else. Then they flip this electron, and that one flipped too. And they're like, what? How could it do that? Somehow this electron over here knew that this electron flipped, and it flipped too. Even though they're separated, it's totally not even part of the system anymore. How did that happen? Okay, that's string theory, spooky action at a distance. There's all kinds of things in quantum mechanics that are very strange. They're really cool too. And even in my field in electrical engineering, we have a thing called a tunneling diode. A diode is a device that allows current to flow one way but not the other. Normally, when you see an electron flowing the right way, it starts at the beginning, you can trace it through, it comes out the other side, makes perfect sense. A tunneling diode, that barrier there, very strange. The electron comes in, then it disappears and pops out the other side. Weird. It's a tunneling diode. Can't explain it, but we use it all the time. Kind of cool. Quantum mechanics. So, using quantum mechanics, we get these magical quantum fluctuations that happen. Can't explain it. It's okay, though, because quantum mechanics is weird. Somehow, it just started the whole thing. And that's okay, because it's quantum mechanics. Maybe there was a previous universe. It was out there, collapsed, turned into a big black hole. All of a sudden, it exploded. That was the beginning of the Big Bang. Problem solved. But where did that universe come from? Not my problem. I wasn't there. I couldn't see it. I don't have to explain that, right? Multiverse theory, parallel universes, same thing. What created them then? They all have the same problem. They're just kicking the can down the road or pushing it out of view. That's not my responsibility to answer that. The Bible and scientific evidence show that there was a beginning, but only the Bible explains how and why. Okay, so we're ahead of them. And there's Genesis 1:1. That's where it came from, right? Okay, initial spontaneous star formation is another problem. We kind of talked about that a little bit already, but if you take a balloon and you blow it up, it takes some work. Those molecules, they don't want to be together. You got to force them to. Now, part of that pressure that you're exerting is stretching that rubber too. But if you take like a Ziploc bag or something that's not stretchy, you blow into it, it's pretty easy until you get to a point. Now, you're forcing those molecules to be jammed in there, and they don't like that. It takes work to get them together. And they say, well, there was just so many of them out there. There was this center of mass. It just kind of pulled in. But the amount of mass that's there, the gravitational force on those individual parts is like minuscule. Okay? There's just no way to explain how you're going to get all that stuff. Forcing these molecules together that don't want to be there, forcing them enough to undergo nuclear fusion. There's just not really a way to do that. And I kind of alluded this before. They say, well, there must have been some sort of pressure wave that happened. Well, where would that pressure wave come from? Well, there was a supernova from a star collapsing, and that caused it. Okay, well, where did that star come from that caused the supernova? Well, it was another one before that. Where did that one come from? And there's no end to it. There's no way to explain how that very first star underwent nuclear fusion. There's just no way to explain it. At least I haven't seen a good explanation of it anyway. Missing antimatter. There's a lot we could talk about this. I don't know if anybody's heard of antimatter before. It's a Star Trek thing, right? But it's actually a real thing. They've done experiments in the lab. When you have matter, if it spontaneously arises, mathematically, you have to have conservation of mass, conservation of charge, and all that stuff. You have to have antimatter. They've done experiments in the lab that shows that. Problem is, when you have antimatter and matter, they tend to really want to get back together, and then they annihilate each other. Okay? They've seen that kind of thing happen in the lab. So as you look out into outer space, though, lots and lots of matter, almost zero antimatter. What happened to the antimatter? Absolutely no explanation. Should it be there or not? Yeah, it seems like it should be, but there's no evidence of it. Where did it go? Okay, they can't explain that. And this is really actually a huge problem. Horizon and flatness problem. I debated whether to even put this one in there, but it does come up again, so I'll just talk about it briefly. This gets back to that cosmic background radiation. We talked about the bathtub. Now, if you're stretching out this bathtub all the way across the universe, billions of light years away, it would take a long time for that energy transfer to occur all over the place to make everything that uniform. Okay? You would have to go faster than the speed of light to do that. You just can't do that. So they said, well, that's where this rapid expansion thing came in. Very early on, all that energy transfer happened really quick, so when it started expanding, it was already even. Okay, so that rapid expansion kind of explains that. But that introduces all kinds of other problems. And even like we talked about orbits of things, if it's a little too fast, it flies out into space. If it's a little bit too slow, it crashes into the sun. When you have this expansion of space and the way they say that things are being brought into existence from energy into matter and stuff like that, that is a super, super delicate balance. It's got to be finely tuned or it's going to crash. They've done all kinds of mathematical modeling, lots and lots and lots of ways to fail, really only one way for it to work. That's the horizon problem. Fine-tuning, kind of tough to get away from that. So that is an issue there. It's not necessarily easy to explain, but they've looked at the math and looked at the data, and their theories are off by an order of magnitude, which in the engineering science world, that's a big deal. 10 times error, that's huge. Okay, so they really had to work with, they tweaked these cosmological numbers and stuff to make it work. And I got a lot of my stuff from Jason Lisle. He's a Christian astronomer. He works with the Answers in Genesis people. He's written quite a few books, but this is the way he worded it. This basically disproved the Big Bang model, and it really should have been abandoned a long time ago, shortly after it came up. But they just don't have anything else to replace it with, so you got to tell them something and just ignore that part of it. Why is the universe expanding? We kind of talked about this already. If you have mass and you need to move mass, it takes a force. Forces come from energy, so if the universe is expanding and moving all that mass, there must be some sort of energy, no idea where it's coming from, can't see it, so they call it dark energy. Okay. But as we'll look at some Bible verses, it does talk about God stretching out the heavens, and he says that multiple times. So if the heavens are actually expanding, and we've seen redshift of it that would support that, we have an answer for it because God's doing it. Okay? Here's a couple. Right from Genesis, let there be an expanse in the midst of the waters, let it separate. So that's an initial expansion right there. Started out, there was the deep, the Holy Spirit, the Spirit of God was hovering upon the face of the deep, which is the waters, the abyss. We think this is where, as I said in one of the previous sessions, that this is where God instituted the laws of physics and created matter and all that stuff, and then he separated it and stretched them out into the lower and the upper waters, an initial expansion. In many other places, and he called the expanse heaven. And then Job, he stretches out the heavens, treads on the waters of the sea. That goes back to the first couple of verses of Genesis. He is the maker of the Bear and Orion and a Pleiades. What is that? Anybody heard of those before? Tom? Okay. All right. Here we go. Ursa Major and Ursa Minor. Those are the bears. Mama bear and baby bear. It's kind of hard to see, but there's Mama bear and there's the baby bear. Ursa Minor, Ursa Major. Those are the big and the little dippers. And the stars on the end of the bowl of the Big Dipper point over to Polaris, which is otherwise known as, anyone? Polaris, it is known as Polaris, yes. It's also the North Star, that's right. And what that means, you look up and the North Star is always in the North Star, but all the stars rotate around it as the Earth rotates. So different times of the year, different seasons, you'll see the Big Dipper up, and then later, 6 months later, it'll be down below. It's kind of cool. Okay, constellation of Orion, otherwise known as the Hunter. That's what it looks like. It's a really beautiful constellation. This is kind of what it looks like. There's his bow, and then there's his belt, and there's actually 3 stars hanging down, which you can see there. That's his sword. There's nebulas in there and all kinds of cool stuff. Excuse me. The Pleiades, it's also called the Seven Sisters, and it's given a number. It looks really big there, but if you look at it in the sky, it's actually very small, but it is really pretty. Those stars are very pronounced. They have a really unique color, just really pretty. And it's right there in Job. And, you know, Genesis is the first book in the Bible, but it wasn't actually the first book written. If you look back, Job was written before that, actually. So very old. I think, if I remember right, it was probably 500 or 600 years earlier than when Moses actually wrote Genesis, the Torah. So it's pretty old. You know, if he's in the Bible and is really old, he's probably not very smart, right? I don't know. You look back and stretches out the heavens. They were talking about redshift way back in the day. These guys think they're so smart. They're way behind schedule. And they knew about these constellations and stuff like that. And there's another verse that's coming up too that's going to be really cool. Here it is right now. You know, there's an idea that if you're a creationist, you're a flat earther and all that kind of stuff. That's not in the Bible anywhere. You know, there was a problem with Galileo back at the early church. Unfortunately, because of what they did to Galileo, you know, all the church, they're flat earthers, they're old science, they don't know what they're talking about. And they apply that to everybody, but there are lots and lots of scientists that are Christians. That's a stupid thing for them to say. Nowhere in the Bible does it talk about flat earth or anything, right? Look at some old cosmology pictures, you know, Greek mythology. How is the earth being held up? Oh, Atlas is doing it. Well, what's Atlas standing on, right? I think it's a Hindu mythology. There's the earth that's being supported by a bunch of elephants. Well, what do the elephants stand on? It's a big turtle. They're standing on the turtle. What's the turtle standing on? Oh, no, that's out of view. We don't show that part. But what does the Bible actually say? Again, back in Job, he spreads out the northern skies over empty space. He suspends the earth over nothing. Sounds like it's floating in space. It's not resting on anything. That's what the Bible says. Okay? He knew. They weren't stupid. Lots more Bible. I'm not going to read them all. Stretching out the heavens. In Isaiah, the circle of the earth. I tried to look. I have that Strong's Concordance and the Hebrew Lexicon. I had those books here before, super thick, all kinds of Hebrew words and stuff in there to try to look up sphere, to try to argue against the flat earth thing. Sphere is actually a Greek word. If you look in the Hebrew, I did not find the word sphere in there. They have circle and ball. And you look through circle, one of the definitions in there is a ball. They understood. To them, it was more real life to have an orange or a ball or something. Drawing a flat two-dimensional circle on a piece of paper, that was kind of out of the ordinary. So the way I took it anyway, the way I understand it, is when they say circle, that's understood to be a round thing in three-dimensional space. Okay, so if you apply that there, he sits enthroned above the circle of the earth. I take that to mean they understood. It was a three-dimensional thing, a ball, not a flat thing. Okay, that came later. That was somebody else's idea who was not actually reading the Bible. More stretching out the heavens. Zechariah, same thing. Okay. And not only did he create the universe, he didn't just walk away and leave it. He sustains it. All kinds of Bible passages talking about holding things together and all that. And then in 2 Peter, but by his word, the present heavens and the earth are being reserved for fire. Does that mean after we're done going through expansion, one day they're looking, oh, we don't have redshift anymore, we have blue shift. That means things are coming in instead of going out. That can't be good. I don't know, I'm just tossing that out there. Maybe that's the big crunch at the end, and if there was this bright light and all this thermal nuclear stuff going on at the beginning, when it comes back to the big crunch, it's going to happen again, and it's going to be pretty fiery. I don't know, I'm just throwing that out there, but that's what it says anyway. It's being reserved for fire. Okay, dark matter. We talked about dark energy. There's this dark matter thing they had to invent to answer some questions. Remember when I was talking about the planets and their velocities and all that stuff out there, the ones that are further away go slow because the gravitational pull's not that strong, so it doesn't have to go that fast. If it did go too fast, it would fly off into outer space. So there's this delicate balance there, right? And there's equations that you can use to calculate what it should be. In close in, it really follows that. They have all the distances, the astronomical orbits, and the periods, and it follows really good. Notice this isn't a logarithmic scale, though. What that means is each division is not like 1, 2, 3, 4. This is times 10, times 100, times 1,000. So it's like really growing fast. Okay, but if you do the math and plot it out, it's a nice straight line. But when they notice that when you're looking at things that are really big, like galaxies, you would think then the outside stuff's going really slow, and the inside, the closer you get, it's going faster and faster. And that's why you have this pinwheel shape. Okay, that kind of makes sense. But if this has been going on for billions and billions of years, it would start to wind up after a while, and you wouldn't see these arms anymore. It would just be a mess. Okay, how do you explain that? Well, they did some measurements and stuff, and they found out for some reason these things aren't going as fast as they thought. Well, the first explanation is it's just not that old, so you don't have time for all that galaxy wind to occur. But then they did some other experiments, and I don't know if it was confirmation bias, measuring masses and all that kind of stuff way out there is kind of challenging, so maybe they're not accurate, but they're seeing that it's not following the pattern of what they thought. It's actually going faster out there for some reason, which makes no sense. So they decided, well, there's got to be some sort of matter out there that's screwing things up. They look for it. They can't find the matter. They call it dark matter. It doesn't give off any radiation. You can't see it. But in order to explain why that's happening, it has to be there somehow. Okay, so it's another one of those theoretical things. Okay. Okay, this is just more of the same thing, dark matter. More on dark matter. Is it real? If it is real, 80% of the matter that's out in the universe is dark matter. 80% of it. That means only 20 of what we see, that's only accounts for 20% of the universe. Could be, maybe God's using that for something, but it does seem a little bit suspicious. Let's see. Okay, back to the comets. We already kind of talked about that. Since comets are shedding material, after billions of years, they should be gone, but they're not. They're still there. Easy explanation is, it's not the solar system, the universe is not billions of years old, it's only 6,000 years. Not a problem. The Oort cloud, just more on where that is. I'm not going to go over that again. More on that. Asteroid belt. We kind of talked about that already. Let's see, what time are we at? 20 minutes. Okay. Kind of the bottom line there is after all this time, why isn't something captured and why are they still there? Why isn't there any even hint of a protoplanet in there anywhere? It's almost like, I thought, well, how do you explain that? And I'm like, well, maybe God put it there to show them this is what happens when you have randomly distributed rocks. They stay that way. Your explanation of how planets form really doesn't work. And I've tried to argue that with people before, and they're like, well, you have all the perturbations of gravitational space from Jupiter and all that, it pulls them out and pushes them in and all that. And after billions of years, this is what it's going to look like. Really, I have not seen one mathematical model that would explain actually how that happens, because if you think, all right, you have, let's say you do have this proto-planet starting on this side of the sun, and you have all this debris over on the other side of the sun. Somehow it has to get from here over to there. Now, if it's in a stable orbit, you have to disturb that, and you have to accelerate it so that it gets fast enough to go around. But if it's going fast enough to get out of orbit and go around, then it's going to want to fly off into space. So you have to have another force that's pushing on it, not so that it doesn't do that. Then when it gets close enough, you have to actually slow it down so it doesn't bypass. So now you have to apply another force to get it to slow down, and then it can't crash in there too hard or it breaks up, bounces off, all that. It's got to crash just right. How do you explain that? And I've never seen any mathematical models that actually describe that, how that happens. So.
Is that how a typical lunch break at Keyport goes?
Yesterday we had our potluck for Christmas and stuff, and we were talking about some things, but three-dimensional space did come up during the discussion. So. I'm okay with that. Now with the James Webb Space Telescope that we're going to talk about in a minute, they've been able to see way, way out there. And they've actually seen, either directly or indirectly, that there are other stars out there that have planets on them. And they expected, based on how, the model that I showed about how planets form and solar systems develop and all that kind of stuff, you have the rocky planets on the inside, you have the big gas giants on the outside, and they can explain why that happens. The science is settled, that's the way it works. Now they're seeing these other things, and the gas giants are huge, and they're really close to the sun. And then there are some rocky planets, but they're outside of that, and they're like, uh-oh, that doesn't follow. How are we going to explain that? And there's some other issues, like there's one that they've seen just recently, where there is a rocky planet, and it's really close to the sun, and it's really huge, and it's actually way too big for the sun. Like in our solar system, the sun is 109 times bigger than the Earth, massive compared to little Earth. In that solar system, it's the other way around. Not the other way around, but the sun's still bigger, but the Earth is like kind of like a little brother, not some little speck way off. And they're like, that just can't be. And so what they're saying, really, and this is a traditional scientist, it's not a creation scientist or anything, but he's saying we need to re-examine our understanding of how planets and stars form. I mean, he's admitting the science is not actually settled because they're finding very surprising things. Okay. But to be honest and fair, they have found some solar systems out there that kind of look like ours, and there's some Earth type that are in what we call the Goldilocks zone, where it's just right. We showed the pictures of how awful the other planets are, and then all of a sudden you get to Earth and just absolutely beautiful pictures, and that can happen because it's in the Goldilocks zone. It's not too hot, it's not too cold, the radiation, we have our magnetic field and all that, it's just right. And so they have found some planets out there that are in that Goldilocks zone. That doesn't mean that there's life there, though. But sometimes when you really read into it, though, it's not as great as it sounds, but that's what the headlines would lead you to believe anyway. And there's a bunch of references there if you want to look into that. Here's one with the moon I talked about. When they went to the moon, and yes, I'm pretty sure that they actually did, and they put mirrors up, and then they can shine lasers at those mirrors, and they can measure the distance from the moon to here, and they found out that the moon is actually escaping us at about an inch a year. And they're like, that's weird. So first of all, I don't know how you explain that. But is that really even an issue? Well, again, if you go back in time, if it's been moving away as you go forward in time, as you go back in time, that means it was a lot closer. And in 6,000 years, that would only be about 800 miles. Not a big deal because the moon's about 250,000 miles away, so 800 miles is no big deal. But if you go back billions of years, I think, I don't remember the amount of time, did I say up there? at any rate, if you go too far back in time, then possibly the moon would have been touching the Earth. What point? 1, 2, 3, 4. Yeah. Yeah, 1.5 billion years the moon would have to be touching the Earth. I mean, and that would be impossible, really. I mean, how do you explain that? Okay. So that's another one that can't be explained based on actual measurable things that we have seen. Yeah, there's some, I don't know about the Gulf of Mexico, but there's some theories that a big asteroid hit the Earth, broke off a chunk, and that's kind of what became the moon. That's a good question, though. This question was, wasn't there a theory that somehow the moon was formed out of the Earth around the Gulf of Mexico? Somewhere around there, and so I said, yeah, I haven't heard the Gulf of Mexico explicitly, but they think that that's where the moon came. A big asteroid came and hit the Earth, broke off a chunk, and that became the moon. So there are those theories out there. Yep. Yes, conjecture is another word. Yeah, and if you don't know what conjecture is, that's like, say you're in a trial and somebody comes up with an idea to prove why his client is innocent, and he just made it up to make it sound good, and then the prosecuting attorney says, Your Honor, I object, that's conjecture, there's no evidence for it, it's hand waving, the judge says, objection sustained, dismiss that, then there's no evidence for it, we can't use that. That's conjecture. Okay, so good point, Tom, thank you. Okay. We also get into the synchronous rotation of the moon. That gets back to the far side, near side kind of thing. There's some ways to explain that. The way the craters are, that's tough to explain too. I have some ideas about that, but I have to research it to make sure I'm not making stuff up and doing what they're doing. But we'll talk about that when we get into geological evolution. But this was an interesting thing I found. Harvard, our professor Harold, who is also of Apollo, reportedly said, it is easier to pretend the moon is not in the sky than to explain how it came to be there. There are a lot of difficulties explaining how the moon actually got there. How is it in stable orbit? Why is it slowly drifting away? And how could it do that for billions of years? So they admit that there are problems with it. Okay, so we talked about the James Webb Space Telescope. The big telescope used to be the Hubble telescope, but there were some issues with it. It did a great job, but there were limitations, I should say, not issues. Just do this real quick. The one on the left is a picture of this nebula taken by the Hubble telescope, which looks great. It's beautiful. But the one on the right is from the James Webb Space Telescope. And you can just see through some of this material, and there's so many more stars, very clear. And the more stars you can see, the further back you can see in time, as it were. So back up one here. So they're saying they can see back so far that we're seeing like 13.1 billion years ago. Is what they think. And if you recall, the magic number for how old the universe is 13.77 billion years old. So that's pretty close to the beginning of the universe. So if you're looking back in time, because it takes time for all that light to get to us, and you're looking at the beginning of the universe, you would expect to see certain things based on the theory. Okay, but what they're seeing is very shocking. And they're saying that we just discovered the impossibly early, impossibly massive galaxies. There's a reference for that. I didn't make that up. It's not some creation website. I mean, that's like real news, right? So they're finding out there's some problems. They should be seeing tiny young baby galaxies. That is not what they're seeing. Oh, yeah, okay, so that's kind of what there shouldn't have been time for those galaxies to have formed. They're even finding massive black holes. We'll talk about black holes here in a minute, but Black holes are basically stars that have collapsed. They've run out of fuel. They've collapsed. Lots of gravity in a small point. Keep sucking more and more matter in. Gravity field gets stronger and stronger. Gets bigger and bigger until finally it gets to a point where it's so big, so massive, so much gravity, not even light can escape. Radio waves can't escape. Nothing can escape from this thing. So that should take a very, very long time for a black hole to form like that. So if you're looking way back in time, you should not see any black holes. Not only did they find black holes, they were huge, massive black holes. And they're just like, how do you explain that? We're looking back in time and we are seeing things we should not be seeing, but they're there, okay? And so then there was, and the James Webb Space Telescope only went out in, it was December 25th of 2021, so it's not been out there very long, but they're already finding these things, and when they came out, oh man, people are just exploding. Big Bang Theory's broken, and all that stuff, and it depends on who you read. They're like, oh, it's not broken, it's not broken. We just gotta tweak it a little bit to explain that. Everything else is fine. You know, don't look behind the curtain, it's fine, you know, kind of thing. And this, it's kind of hard to see there on here, but this was a post from an astrophysics professor at a university, and she said, right now I find myself lying awake at 3 in the morning, wondering if everything I have ever done is wrong. And she said, I stand by that statement. I mean, that's sad. To think your whole life and your whole meaning of existence has just been a waste of time because of something that you saw from a telescope, because your beliefs are being crushed. You know, that's how upset some of these people are. And then you get, you know, like I said, some people are like, it's not that bad. I don't know, does anybody know who this guy is? Neil deGrasse Tyson. He talks about it a lot. When you looked at the first YouTube videos he put out, he was one of those, oh, it's not broken. We just need to, you know, make any excuses for it. I just watched one the other night. That's where I got this picture from. And you can look, he's a little bit tired there. And he's just like, man, this is wearing me out. I'm just getting to the point I don't know what to say, you know, kind of. But he still defends it. So it depends on who you ask. And I have a couple of references here, and they're down here, so I'm not making this up. But at face value, this means the Big Bang Theory is wrong. It's broken. There's something seriously wrong with it. Plus all the other things that we talked about, and there's a bunch more that we didn't talk about. You know, so when you're talking to somebody, you know, we're getting into apologetics and that sort of thing, and they're bringing up all this stuff, you do not have to have that cognitive dissonance feeling because it is broken. They might not believe that, but you know that it is. Lots of other people know that it is, and you can just calmly stand there and listen to them say. But, you know, this is where it becomes important as Christians to be aware of this sort of thing so that you can start talking about certain things like, you know, multi-dimensional space and time dilation and all that kind of stuff, which we're going to talk about here shortly. And they'd be like, what? I thought you were a flat earther. And you're like, no, I don't know where you get that idea from. But, you know, you can start talking about things and you'd be like, wow, what else do you know? What don't I know? You know, and like I said, that's a golden opportunity. You can stay calm about it and just have a rational discussion. You don't have to beat each other over the head. Right. Speak the truth in love. Yes. Okay. Now, here's one thing that they will bring up all the time that you creationists cannot answer. It's called the distant starlight problem. The universe has to be old because we can measure distances to these other things. We know how fast light travels. So it has to have taken a certain amount of time for that light to get here, and we can see it, so that is proof. You cannot answer that. If it's 1.5 billion light years away, that means that light started 1.5 billion years ago, and that couldn't happen in 6,000 years, so you're wrong. Okay, that's the way that argument goes. Oh, let's see, how much detail do I want to get into? Okay, we're getting close. And so, yeah, if you do the math, it's easy in a simple way. If you're, the distance between 2 points is 100 miles and your car is going 50 miles an hour, you do the math and it's going to take 2 hours. You can prove that experimentally and scientifically, and it makes sense. The math makes sense, okay. But when you start talking about these other things, it's a little bit different. Now, Polaris, if you remember that, the North Star, part of the Little Dipper, 2.6 trillion miles away using the parallax method. So we're reasonably sure that that's pretty accurate. You can use trigonometry and stuff to measure that. If we know how the speed of light, then we can calculate using this equation here. And the light from Polaris left about 400 years ago. That's not a problem. Okay, seems a little weird, but it's not a problem. Now, if you go to the Andromeda Galaxy, and the Andromeda constellation, and in there is the Andromeda Galaxy, otherwise it's known as M31, they take their measurements and they find out it is 14.7 million trillion miles away. That is a long time. I don't know, how many zeros is that? That's like huge, right? Okay, so if we know that the speed of light is such as it is, then supposedly it took 2.5 million years to get here. It's 2.5 million light years away. We can see that star, we can measure it, we're pretty sure that's how far away it is, speed of light, we know what it is, it's been measured experimentally in the lab. How are you going to explain 2.5 million years? That does not fit in 6,000 years. That is a little bit of a challenge. Thankfully, though, we do have Christian scientists who are interested in, they believe in 6,000 years, six-day creation, and they also are very familiar with Einstein's equations and all that kind of stuff. They're also very familiar with quantum mechanics, so they're working on it. But this distance light thing, I kind of talked about it before with the cosmic background radiation. In order for the hot and the cold to even out like that far away, the energy transfer would have to be faster than the speed of light to do that. They can't really explain that. They did it with the rapid expansion thing, but like I said, it came up with some very special tuning. That's the flatness in the horizon problem. And the other thing, and this is where it gets really interesting, time is relative. Of course, time flies when you're having fun. If you're having a bad day, it seems like it goes on forever. That's not what I'm talking about, even though that's a real thing, right? Time is I did it again. Okay. This is called time dilation. It's affected by velocity and gravity, and this has been measured experimentally, happens all the time. This is a real thing. Gravitational time dilation, basically, if you're in a very strong magnetic field, time passes at one rate. If you're outside of that, it appears to travel at a different rate. So a clock that's close to a massive body would record less time than one that's situated far away from it. So in other words, time goes slower in a strong gravity field. And they've measured that. I'll explain that in a second. The other one is velocity time dilation. Basically, the faster you go through space, time goes slower at higher speeds. How in the world would they know that? Well, the first one with gravity, they noticed that with very accurate atomic clocks, they get them synchronized, they're down on the ground, and then they went up, and there's this observatory in Switzerland, I believe it is. It's up in one of the mountains. It's very high up. And then they compared the times then, and it was different. That's weird. Bring it back down. Yeah, they're still working, but why is there a difference in time? And they're looking at some of the equations, and Einstein talked about this. Gravity distorts time. There's time dilation due to gravity. It's been measured. Now you get up into the space shuttle, or the space station, you're even further away. It's even more noticeable. And on top of that, the space station, well, depending on what orbit you're in, but a general orbit to be that's stable out there that a lot of things are in, they're going 17,000 miles per hour. They've measured even more time dilation. It has to do with the velocity and the gravity field. It is a measurable thing, and it's so noticeable that your GPS satellites, that your car follows and your phone and everything else, that information comes from satellites, and it has to have very accurate clocks to keep track of where they are in space and what time and everything. Those clocks were constantly getting off because of time dilation. They have to constantly update them. Now, from the satellite's point of view, his clock is like, there's nothing wrong with my clock. Why do you keep adjusting me? You're the one that's off. Okay, so it has to do with your frame of reference. But since we live here, we're the right time. So your satellite, GPS satellite, we're going to correct you. Okay, so that's what happens there. So it's a real thing. It is a real thing. They've measured it. They can explain it mathematically. It is really weird, but it's there. Okay, now why would I be bringing that up? Because it's going to get even weirder, and you need to like have a feel for this before I get to the next thing. We talked about black holes a little bit, and they say that a black hole is a region of space-time, and notice that's one word, but it's 4 dimensions, 3D space and time. So there's that time thing coming in again. Gravity is so strong, nothing, including light, can get away. They've detected them out in space in multiple places. Okay. You say, well, if it's a black hole, how can you see it? Well, they use radio telescopes to do it, and they convert that image into something that we can actually see because we can't see radio waves, right? But anyway, when you do that, that's what one looks like. This is an M87. I watched a video on this on YouTube. It might have even been on Netflix or something like that, where they explained how they did this, and it was really interesting. They were really proud of themselves, and they should be. That was an incredible feat that they did to collect this image, and it behaves like they expect the black hole would behave. And the thing is no matter what direction that you look at it, that's what you're going to see. You know, like, well, there's an orange disk around it. As you look to the side, isn't there going to be this orange line? No, it's weird. Gravity is so strong there, it actually can distort light and bend around it, and all kinds of weird things. And so this is where it gets even weirder. There's this thing called the event horizon, and maybe you've heard about it in science fiction movies and things like that, right? But it's a really weird thing that as things get sucked into the black hole, you reach a point where, because of the gravity, you're going really, really fast. So that's distorting time, and the gravity field is really, really strong, and that's distorting time, and you get to the event horizon just as you pop into it. You're going so fast, and the gravity is so strong, the time basically stops, and you're like frozen in time. But you're going the speed of light, and very bizarre. But now, if you could look back out, and we're out here looking in, and if you could see them just as they cross that event horizon, their clocks are like going really, really slow. And they're looking out, and they're like, man, their clocks are really screaming fast. But no matter what your frame of reference is, if you look at your own clock, it's normal. Okay? It's really weird. But the math supports that. And some experiments they've done in the lab, they're pretty sure that's kind of how it works. So there's this event horizon. Clocks near the black hole, they tick more slowly than the ones out there. If you were to be an indestructible observer or falling into it, I guess I already talked about that. You're not going to notice any of that, but you're going to look out and you're like, your clock's wrong. And then we're looking in and go, your clock's wrong. Okay, frame of reference, and that'll come up later too. Okay. Now, theoretically, you can have white holes too. They operate in the opposite direction. Instead of having a small thing that gets bigger and bigger and bigger, you have a thing that starts big, and it starts, instead of sucking things in, it's ejecting things out. But because it's a really massive thing with lots of gravity, it also has an event horizon. Einstein did calculations on this. The math works out. You can actually have a white hole. The thing is, as it's ejecting matter, it starts to get smaller instead of bigger, and eventually it's going to eject all its matter, and it's either going to turn into something else, or because the event horizon goes away, or it just disappears. So there's no evidence of a white hole, but mathematically it could happen. And these pictures here, that's why I put this in red. I mean, we've never actually seen a white hole, but that's just kind of artistic misinterpretation of what it might look like. But same thing, massive gravity. Clocks outside the white hole would seem to tick faster than on the inside. Observers emerging from the white hole instead of going in would think that they're fine. They'd be like, your clocks are weird. mine's fine. And people looking in as you're just popping out of the event horizon, you'd be like, man, you're messed up. I'm like, frame of reference again, okay? Okay. So, why am I talking about event horizons and time dilation and all that stuff? That gets back to this redshift issue, a way that we possibly maybe explain some of that. Okay, I'm already over time, so I'm going to go fast on this one. There are two theories out there. This was the first one that I read about. Basically, he's proposing that during the day of creation, and reading the rest of his book, it's obvious he's a believer and he believes in 6 days of creation, 6 24-hour days, okay? He's just kind of trying to come up with an idea that using science that would explain the redshift problem. But basically, he uses, the short of it is he thinks one way to explain it is God used a white hole to begin the creation process. Through time dilation, the creation started inside the event horizon. Then as he gets to day 4, he's creating the stars and everything. They pop out of the event horizon, begin stretching space. The light was at the event horizon, but being stretched out, so that's why it's redshift. Lots of time is going by out there, but not in here where we are. Then we pop out of the event horizon. The universe is already there. It's just really far away. We see lots of redshift. Seems like a kind of cool idea, but there are a lot of issues with it, which I'm not going to get into. And so here we come up with the second one. It's similar to the white hole theory, but it doesn't actually use a white hole. Basically, the first 4 days of creation, he's saying, are just like it says in the Bible. Okay. Now, we kind of talked about this a little bit in some of the earlier ones, but there's the initial expansion when he used the firmament to separate the waters from the waters and that sort of thing. We saw in a bunch of other Bible verses, God stretching out the heavens. Is that the same stretching that happened with the firmament, or was that something that happened later? We don't really know for sure. We got to be careful what we say about it, but here's one idea. He's saying that early on, during the first part of day 4, there was the firmament, there was the waters outside above the firmament. He used that material then because in the Hebrew language, there's a difference between created in verse 1 versus created or made things later, because he made the first creation is made something from nothing, and later he created or made things from materials that he had already made earlier. Thank you, Chris. From creation, not stuff that was just laying around, right? So he made the stars and the galaxies and all that stuff, but they were closer to Earth to begin with. Then he began stretching out the heavens. By the end of day 4, everything was stretched out. We can see the light because it started there. It's red-shifted. You don't need a white hole. And using some of his 4D and 5D space velocity, not just space-time, but space velocities, and then 5D is space-time velocity. It solves a lot of the problems that the white hole theory had. As you really look into it, it doesn't violate the known laws of physics. It agrees with Einstein's laws. It also doesn't conflict with the Bible, so it's a really cool idea. I kind of wanted to develop it a little bit further, but I'm still working through the math. He actually includes math in his book. And I like math, but I have to say I was starting to sweat a little bit as I'm looking through these equations. And I'm like, man. And you get an equation and it has a term in it, and that term actually has its own equation, and it just, wow. But he did do the math at least. Okay, so I think that this is probably a pretty viable explanation. It doesn't violate the laws of physics, like I said. It counts for the redshift, the distant starlight problem. It also gets rid of the missing mass problem, strangely enough. I can't really explain that. I don't want to try to until I really understand it. But and what he's saying is the view that we see when we look way out there, it's not shortly after the Big Bang. That's like shortly after creation. What we were seeing is what it looked like shortly after creation, and that's why the galaxies are so big. That's why there's big black holes. There wouldn't be time for it to happen naturally. God made it that way, and we're seeing it. When he said that, I'm like, Okay, maybe you got to be careful about that, but just think about that. If that's true, that is really cool. When you look through a telescope and you see a galaxy out there, you are seeing what God made. I think that's pretty cool. All right. To the conclusions, we're a little bit over time here, but first of all, the Bible is God's word and it stands on its own merit. He does not need us to prove him right. It's true no matter what, and that's what we're going to hang on to, right? But if we can look at things in science and go, yeah, that really tracks, that's a good thing too. And like we talked about, you shouldn't use science to prove the Bible because science changes over time. Very rarely is science ever settled. Somebody comes up with some new theory or a new type of physics comes along. Can't use science to prove the Bible is true. If they agree, that's fine, but the Bible is true without us proving it. Some observations agree, like we talked about, for example, but the difference is why we see them. There was a beginning of the universe. God created it versus no idea, quantum fluctuations or whatever. Okay, we have an answer for it. It is expanding, or at least was. God stretches out the heavens, says that in the Bible. They had to come up with dark energy, okay? So really, God told us what we need to know, how we got here, why we're here, how much he loves us, how we are saved, and where we are going. Those are really the important things. But there is that one Bible passage, I was going to put it up here, that it's like God challenges us. I think it's in Psalms, where something about it's the job of kings and great people to dig into these mysteries. If you can't do it, that's fine. Just, have faith like a child. You're going to heaven. But if God's given you abilities and to think about things and explain things, it's a good thing to dig into these things and be able to understand them and marvel at his creation. That's good too, okay? But we got to keep in mind the Bible is true first, and this is the important thing right here, okay? One last parting shot. I always say, we should be able to give a defense, but do it with gentleness and respect. So this might seem a little disrespectful, but I didn't write it. I just found it. So this John Mather, he's part of NASA, Goddard space flight, and he said, we have no direct evidence of how galaxies were formed, how the first stars were formed without help of other prior generations of stars, how galaxies evolved, whether they were formed from aggregations of smaller units, blah, blah, blah. But basically, the supposed Big Bang. And he's saying that the science is not settled. There's a lot of problems there. Now, in a good way, that gives justification for getting millions of dollars from the taxpayers so you can continue to do research and have a job. Because if everything really was answered, why study it anymore, right? But so there's that. And that's from him, that's not from me. Then there's this Lee Strobel, if anybody's familiar with him. He's a Christian. He's written many books and stuff like Case for Christ. He goes through sort of a very analytic view of, is Jesus made up? Or if we look at the historical records, can we actually believe that he's there? And that's what his book, Case for Christ, is. And it's compelling, even from non-biblical sources, that Jesus of Nazareth was a real person. And there was lots of stuff talked about him. But anyway, what he has to say, to continue in atheism, I'd need to believe nothing produces everything. Non-life produces life. Randomness produces fine-tuning. Chaos produces information. Unconsciousness produces consciousness. And non-reason produces reason. I just didn't have that much faith. So I thought that was kind of a clever way to say that. Okay, that's it. That's all I've got. Thank you. We went kind of fast.